Yep.
Okay, so here's seminar 3 of the network theory seminar. So notes are continuing to come up online. I just put notes for this class up on my blog, and I'll link to them from the network theory page. Okay, so what are we doing? So we've built up a category, rescirc, where the morphisms are circuits made of resistors, electrical circuits made of resistors. So let me say it a little bit more mathematically. So the objects are just finite sets. So you imagine a bunch of dots as an object. And then what's a morphism from one finite set to another? So like here's a morphism from a 3-element set to a 4-element set. So the action is in the morphisms. So a morphism from some set I to some set O is, well, it's actually an isomorphism class of cospans. So don't worry about the isomorphism class stuff too much first. So it's a cospan is a diagram where you have two objects mapping to some third object called the apex of the cospan. And this is a diagram here, not of finite sets, although you might have guessed that if you attended the last class. It's actually a diagram of labeled graphs. So this diagram here is in the category of graphs where the edges are labeled by resistances. A resistance is a number 0 to infinity. And so how do you think of a finite set as a graph? You think of it as just a set of vertices. You think of it as a graph with no edges. So they are sort of degenerate cases, but the more interesting piece is the middle. So gamma is this graph. So it consists of a set of edges, E, a set of nodes, N. Every edge has a starting point and an ending point, so it has a source and a target. And then every edge has a label called its resistance, which is a number from 0 to infinity. So I and O are also structures of this type, but they're structures where the set of edges is empty, so these functions just become the only possible thing they can be. They become boring. Okay, so that's what we've got. And so the picture of a morphism is what I started to draw here. I is some set, O is some set, and then we've got our electrical circuit. We'll have a bunch of other nodes as well. So that's the idea, and last time I went into that in a lot more detail and explained how you actually make it into a category. That is how you compose these morphisms. I didn't prove that composition was associative, which is sort of the most important part of checking that you've got a category. So it sounds like what's going to happen is that next week Franciscus will give a talk about that type of thing. So Franciscus has been working on this kind of thing, but he's been getting around this irritant, this isomorphism class baloney, by working not with categories, but with bicategories. So there's something better than a category called a bicategory, where you have objects, morphisms, but then also two morphisms, which are morphisms between morphisms. And those two morphisms would be, for example, isomorphisms between cospans. So we would actually keep those into the structure we're studying instead of doing what we're doing right now, which is just to say whenever two circuits are isomorphic, we treat them as the same. So if you take the bicategorical approach, we could distinguish between this circuit and some isomorphic circuit and say they're different, but they're isomorphic. Anyway, so he'll talk a bit about that in some way or other. But what I want to do now is to actually go ahead and say, okay, so what do we do with these electrical circuits? So what do you use an electrical circuit for, and how can this formalism help explain that? So what you do with the circuit is you put some current through it, feeding some current into these nodes here. Or another way to think about it is you set the value of something called the electrostatic potential at these terminals, these special nodes here and here, and then and that typically will determine what the current is. So to use a circuit, we put a potential and current on each terminal. So let me define the concept of terminal. So the set of terminals is the image of, well, I didn't name these functions. There's a function I mapping the inputs into the set of nodes of our graph. Similarly, a function O. So the terminals are the nodes that are in the union of the images of those two functions. There's a little bit of a nuance here, which is actually turns out to be really important, but I don't want to dwell on it overly. But sometimes if you don't dwell on anything, sometimes if you don't dwell on something at all, people will worry about it. So there's a distinction between the set I and the image of the set I in T. So here I've drawn them so they look just the same. You see these three dots? I said it was I, but I also sort of drew it as if it was the image of I inside the graph gamma. And that way of blurring the distinction is not so bad if the function I is 1-to-1. If the function is 1-to-1, then there's a 1-to-1 correspondence between the set I and its image inside of N, so you don't have to worry too much. But actually, I never said that the functions I and O have to be 1-to-1. So if they're not 1-to-1, then the picture is a little more misleading. We could have several, quote, inputs, all of which are mapped to the same point in our circuit. That may seem like a really dumb idea or a really weird idea, but it turns out to be an incredibly useful idea. And it's an example of the general philosophy that putting in extra clauses in your definitions to exclude things that seem weird to you just because they seem weird is usually a bad idea. You at least investigate those weird things, and they often turn out to be really crucial. Just like the empty set seemed weird until someone realized, hey, it's a set like everybody else. It's good to have it in there in our collection of sets. So anyway, so this is why I'm saying I union MO instead of just I, capital I, disjoint union capital O. Okay, but anyway. So what we do is we put a potential and current on each terminal, but the interesting thing is you can't just put any old potential and any old current on each terminal. As I said, very often if you put potentials on the terminals, that will determine the currents. So only certain choices are allowed, and that's what I want to explain. And in particular, this set of choices that are allowed, that's what we call the behavior of the circuit. This is the the set of these, the set of allowed ones, tells us what the circuit does. So I'm taking the poor old word behavior and turning it into a sort of mathematical concept for now. Maybe if I wanted to be a bit better, I would call it the external behavior of the circuit. That is, the part of what the circuit is doing that you can notice only by looking at what's going on at the terminals. We think of the terminals as the sort of edge of the circuit, the part that you have the ability to access. So we very often will think of a circuit as being black boxed. I don't want to waste this precious magic marker by drawing the whole box black, so this looks like a white box. It's a low-budget black box. But if you black box that circuit there, all you see is this. And so you don't know how many nodes there are, how many edges there are. There's a lot of stuff you don't know, but when we develop the rules of the game, what you will know is the behavior of the circuit. That is, we will figure out a rule that lets us calculate which subset of voltage current pairs we can actually obtain. So black boxing a circuit will be the process that gives its behavior. So how does that work in detail? That's what I want to explain. So I have to review for you very rapidly and efficiently a little bit of electrical circuit theory. And the main way I want to think about it is using what's called the principle of minimum power. So the principle of minimum power is a principle that says what a circuit made of resistors does. So what does it do? So we have to introduce what we're minimizing over, and then the power will be a function of that. So when you use a circuit, when you sort of turn it on, you get more data than we've been talking about at first. Namely, we will get a current for each edge, a current running along each edge of the circuit. So each edge will get a real number. So, and I think I'll write the arguments of these functions as subscripts. So I sub E is called, this is just a definition, the current along the edge E. Remember, our edges have little arrows on them. It's a directed graph. So if the current is 5, you should imagine some current of 5 amps, if you care about units, flowing along that edge in the direction of the arrow. And then a second function, the voltage, again assigns a number to each edge. So you call V sub E the voltage, but for some reason people don't say along. It's actually a deep explanation that I don't want to get into. They say the voltage across the edge E. But don't worry about that. That's just the preposition that we choose to use. So then the power, this thing that we're minimizing, what's that? It's a sum over edges of the voltage times the current for each edge. So what's the idea? When you're running electrical current through a circuit made of resistors, the resistors get hot. And so the circuit actually uses up electrical power. Energy is conserved, so the energy doesn't just go away, but it turns into heat. Heat sort of gets wasted. So you're pumping in energy at some rate. Power means energy per time, right? So you're pumping in energy at some rate, and then it's getting turned into heat. It's spewed out by resistors. So like if you put your hand on the back of a television, an old-fashioned television, especially if it has resistors, and it would be warm, and that's the power I'm talking about. And so each edge has a resistor on it, and so each edge puts out some power, and the amount of power it puts out is equal to how much current is flowing through that edge times the voltage across that edge. You can think of voltage as like a change in height. So you can imagine current is like water flowing down a hill, and voltage is how far down the hill goes. So if you have a certain amount of water per time flowing down a hill of a certain height, it loses a certain amount of energy in the process of going down the hill, and this is how much it loses. And current works just the same way, except it's a sort of mystical fact that at every point, well, it's a mystical fact that there's something analogous to the height of a hill, or how far down water flows down a hill, that works for electrical circuits, and it's called voltage. Its existence is cleverly figured out through experiments. Okay, so when I say principal minimum power, I'm going to talk about minimizing this quantity, but so far it seems like a stupid idea, because so far you could make this quantity be as negative as you wanted to. If you got to freely choose I and E, you could make these all be large negative numbers. So far minimization doesn't sound like a bright idea, but the point is there are some relations between current and voltage that make it more of an interesting idea that I haven't told you about. So the first one I want to tell you about, I guess, is Ohm's law, which is an approximately valid law for resistors. And it says that the voltage is proportional to the current, or if you like, the current is proportional to the voltage. Let me think of it this way, that the current is the voltage divided by the resistance. Remember, each edge has a number attached to it in the very definition of a circuit made of resistors. It's resistance. And so this is a law that says if you want to know how much current is flowing down the wire, it'll be proportional to the voltage across that wire. So it's sort of like if your hill goes down further, the water will flow faster. And it's proportional via this proportionality constant. We just define it to be in the bottom of the fraction. So resistance is sort of how hard it is for the water to flow down the hill, or in this case, how hard it is for the current to flow through the wire. So like if you have a wire made out of silver, it has very low resistance. If you have a wire made out of iron, it has very high resistance. You can craft the resistance to do whatever you want by putting in little gizmos called resistors. Okay, so that's already great. So what it means is we don't really need to think about current and voltage separately. We can focus on one, for example, voltage, and write the power in terms of that one. And now minimizing it starts seeming like a less silly idea, because remember the resistances are positive. So this is a sum of non-negative numbers, so it has a minimum. But it still seems like a sort of stupid idea, because you can minimize this just by setting all the voltages equal to 0. So if that's all there was to it, that wouldn't be so exciting. That's perfectly fine. You do minimize power. You get the absolute minimum of the power when all the voltages across every wire is 0, and that means the currents are also 0. That's just corresponds to a circuit that's just sitting there, not doing anything interesting at all. You haven't plugged it in yet, so to speak. So that's the absolute minimum of power. But the interesting stuff happens when we try to minimize this thing subject to some constraints. And that's what we're going to get into. But the other thing I want to say is that we've got these voltages here, but there's another way to think about them due to Kirchhoff's voltage law. So Kirchhoff's voltage law, I don't want to say what it is, but I'll just say something equivalent to it. I don't want to give the standard formulation because it's sort of irrelevant right now. So what it says for our point of view is there exists a function I'll call phi, defined on nodes of our circuit, and it's called the potential, or if you want to be very careful because there might be other things called the potential, we call it the electrostatic potential. I'll just call it the potential. And the property of this potential is that the voltage across an edge is the difference of the potentials at the two ends of the edge. So again, it's just like water flowing down a hill. If you want to know how much down the hill you go from one end of a road to the other, you just take the height at the two ends of the roads and subtract. So this potential here is analogous to height. And so it's a sort of beautiful mathematical fact that throughout all of space there's this function called the electrostatic potential, which we only care about at the nodes of our circuit, but actually in a more full-fledged treatment of electromagnetism, it would be a function on all of space. So anyway, what did I say here? I said such that the voltage across an edge is the potential at one end minus the potential at the other end. There's this arbitrary sign convention here, which, like all arbitrary conventions, causes endless heartache because you can never remember which convention you used unless you stuff your brain with useless information about all the conventions in the world. But anyway, I guess I'll remember it by saying S comes before T. Okay, that's about as good a rule as any. And so that's Kirchhoff's voltage law for our purposes. And so that we can stick that formula in for the voltage as well to get a new formula for power, which is even better. So the power consumed by our electrical circuit is a sum over edges of this difference in potential across each edge squared divided by the resistance of that edge. So I'm going to now mainly think of the potential at each node as the main thing I care about. So I'm sorry, I've introduced like 11 different variables and then like 10 equations relating them, but that means that you can forget all of them except one. Well, unfortunately, just when you've forgotten all the rest, I'll suddenly want to use them again. But anyway, we're going to think of the power of our circuit, power consumed by our circuit, as a function of the potential. And think of this current and voltage as sort of auxiliary quantities. Okay, but I had to use some stuff about circuits to remind you of this formula here. So the idea is that's the power, and so then here's what the principle of minimum power says. So we've got a circuit. We've got certain nodes called terminals that are the image of the functions mapping I and O into the set of nodes. So the idea is we'll fix the potential at the terminals, and then the principle of minimum power tells us what the potential does at the other nodes. So it says given potential V at the terminals, so you get to pick that. Then the potential everywhere else, that is at the other nodes, it has to minimize the power. It must minimize P of V, subject to the constraint that it equals what you said it equals on the terminals. So we're doing minimization with subject to a constraint. Equals the given, equals what we made it equal, equals the given function on T. So you can see that this minimum principle has something interesting to it, because the fact that you're minimizing a sum of squares of differences like this means that each particular edge would be happiest, so to speak, if this quantity was as small as possible. So each particular edge would like the potential at two ends to be equal, but we're imposing a constraint that prevents that from happening. If I put the potential to equal 0 here and 1 here, there's no way the potential at all the nodes can be equal. And so the potential at these two remaining nodes will be chosen to minimize this sum. So it doesn't want to make this difference be too big, because that's going to make the power big. But it also doesn't want to make that too big either, so it has to do a kind of balancing act. Any interesting minimization problem involves a kind of balancing act where you're trying to satisfy two people at once, and there's no way to make them both happy completely, right? And so you can see who matters the most. The ones that, the edges with a smaller resistance will contribute more power. So you have to work harder to make them happy, so to speak. So you will try to make the change in potential be as small as possible. You know, you pay more attention to making the potential across an edge small if the resistance is low. So we could have fun working out a bunch of examples of this, but I don't think I'll do it yet. I think once upon a time I taught a seminar where I did do that. If you haven't ever done it, you should do it sometime. So just like take a simple example like this, put two different resistances on the two different edges here, R1 and R2, put a potential, say, equal to 0 here, and equal to 1 here, and figure out what the potential will be here. Right? If those two resistances are equal, what will the potential be here? 1/2 by symmetry, right? I mean, what else could it be? It's equally concerned with being close to 0 as it is equally concerned with close to being close to 1. So we'll just sort of split the difference and be 1/2. But if this resistance gets to be lower, then this potential here will get closer to 0. So it's some kind of funky average of 0 and 1. Weighted average of some sort or other. Okay, so that's an example. It's good to do to make sure you actually understand what's going on. Okay, so, but because we're mathematicians, we don't publicly admit to trying to understand what's going on. We just spew facts, right? So what we'll do is we'll just take the general situation and figure out what happens. We'll figure out what the principle of minimum power says in general. So let's just see what happens. So suppose V phi obeys the principle of minimum power. In other words, suppose it does this minimization. So how can we figure out what that amounts to? So what we'll do is we'll imagine changing phi a little bit. And if you're at a minimum of some function, when you change the argument a little bit, to first order, the function doesn't change at all. First derivative test. So the idea is, consider any function c from nodes to real numbers that's equal to 0 for all terminals. So this c is going to be a function that we're going to use, roughly to speak, to add on to phi, to change it. But we don't want to change phi at all at the terminals because our constraint says we've fixed what phi is at the terminals. So in other words, we could take any number x, and then what we could do is we could take phi plus x times c, and that will equal phi at the terminals. So we've got all these different possible choices of phi depending on this parameter x. And we want to see what happens when power is minimized at the phi we started with. So we use the first derivative test. The principle of minimum power implies that if you calculate the power at this potential phi plus x times c, and then see how it changes as you change x, this derivative has got to equal 0, at least when x is equal to 0. And then you're at phi. So you're moving along a line in the space of potentials, starting at the point phi. Power is some kind of quadratic phi kind of function, so we're looking for a minimum. We're looking for this function to be minimized along any line of this sort. This would be a consequence of the principle of minimum power. In fact, it's equivalent to it. In fact, this holding for all such c, all the c's that we picked here, is equivalent to the principle of minimum power. Because, well, what could go wrong? Well, the first derivative test is the first derivative vanishing is certainly implied by having a local minimum, but sometimes the first derivative could be 0 and it could not be a local minimum. However, this particular kind of function that unfortunately I erased, this power function, it's a sum of squares of differences, it doesn't have any interesting critical points except minima, even when you constrain it to lines of this sort. So just imagine a function whose graph is like some paraboloid. You restrict the function to some line, so you get some paraboloid of lower dimension, like a parabola. You look for critical points, the only possibility is on the minimum, because the paraboloid's curving up. So that's the principle of minimum power there. That's equivalent to it, that statement about derivatives. And so then you can just work out the derivative and see what you get. So let's just do that. So we can differentiate this power only step is to remember what the power is. So it's a sum over edges of the difference in potential at two ends of the edge squared divided by the resistance for that edge. Oh, whoops. This is the original potential here, sorry. But we've added x. Sorry. We've added x times c, so it's a little more complicated. This is the really want. This is this function at s of e minus this function at t of e. Okay, so that's what we've got to calculate the derivative of. So, but we're really going to calculate this derivative when x equals 0. We only care about what this derivative is when x equals 0. And that makes life a little bit easier, because if you imagine squaring all this crud out, don't actually do it, just imagine it vaguely, right? If you imagine squaring this out, there'll be some stuff that has no x's in it, some stuff that has one x in it, and some stuff that has some x squareds in it. So which one of those do we care about?
One with x.
The ones with one x, right? Because when you're gonna differentiate it at x equals 0. So if you differentiate x squared at x equals 0, it doesn't give you anything. If you differentiate a constant at x equals 0, you don't get anything. So it's only the linear part that matters. So only part linear in x contributes. And of course, linear functions are especially easy to differentiate. Namely, you just remove the x. So we'll do that. Okay, so the part that's linear in x comes from the cross term. So it'll be 2 times this x. You differentiate it with respect to x, and the x goes away. And so we get, oh, now I just remember, I see I made a typo in my blog notes. I left out the 2. Just sort of an annoying 2 there. And then we get the interesting part. Difference phi times the difference c. So this is what needs to be 0 for all choices of psi that obey the condition I said, that they vanish at the terminals. They look like here.
What happened to the resistance?
Oh, they just, I don't know. No, they definitely need to be there. Thanks. Yeah, so this must be 0 for all functions. C, remember, it's a function on nodes, but not just any old function on nodes, a function on nodes that when you restrict it to the terminals, is 0. So let's see if we can unravel this a bit more and figure out what this weird thing being 0 actually means. So to see what it means, we should pick some nice, easy examples of functions psi. Some nice, easy examples of functions that are 0 on all the terminals. So what's a good example to give us insight?
0 on the terminals with 1 everywhere else.
That's one function, but so that's fine as far as it goes, but we need to have lots of them because we want to completely squeeze the juice out of this equation, right? So this is supposed to hold for all psi. So I don't want to do it for all psi. I want to do it for some nice ones. Okay, so I said some nice one. But you were supposed to interpret that as meaning like, and now there are lots of them just as nice as that. And that will be enough to completely figure out what this being 0 says. So he said psi is 0 on all the terminals and it's 1 on all the non-terminals. That's one example, but there's, someone give me a more variegated choice. Yes, Jason?
So put 0 on all the terminals and 1 on one non-terminal, 0 everywhere else.
Yeah, delta functions aren't great, right? So you pick psi to be 0 everywhere except at one node, which happens not to be a terminal. So let's do that. So choose psi be 0 except at one node n, it's not a terminal. See those functions, the functions that vanish everywhere except at one point, they will be a basis for the space of all these functions. So if you know the derivatives in those directions are 0, then you know the derivatives in all directions are 0. So these suffice. And I guess we might as well, I think you said what if we want it to equal at this one node, we'll make it equal 1, just to keep life simple. So it's a Kronecker delta. Okay, so then we just have to see what happens to this thing in that case. So here we're summing over all sorts of edges, but this stuff is going to be 0 here now, unless either S of E or T of E is n, our favorite node that we picked out, non-terminal. So there will be two kinds of contributions to this sum. The ones where S of E is n, and the ones where T of E is equal to n. What about if both S of E and T of E are equal to n? That's certainly possible. Right? You could have an edge such that there was a loop. That would be confusing because then both of these would be there. But then it's 0. So we don't have to worry about them. We could include them or not include them. It doesn't matter that we get 0 for edges where the source and target are both n. So, okay, so for these, for a function of this type, let's see what we get. So first I'll do the sum over the terms coming from an edge where the source of that edge is n. So if the source of that edge is n, and let's say the target isn't n, then we get 1 here. So we get the S of E minus Vt of E over the resistance. And then we do the case where the target of E is our favorite node n, and then we get a minus 1 here. So we get minus some very similar thing. Now it's the target of E. Sorry, lowercase n, our particular node here. So this is what has to be 0. And I repeat that if in the case where both the source and the target were equal to n, this we don't have to worry about. We don't have to worry about that case because it will cancel out anyway. Both in this sum and in the one I'm trying to calculate in the first place. Okay, so this stuff has to be equal to 0. Okay, so the principle of minimum power says if you take any node that's not a terminal, then this crud here has to equal 0. So that sounds fine and dandy, but it sounds sort of confusing or annoying or something like that. But in fact, it's not quite so bad. So someone tell me like how we can think about this, that we can make makes it nicer.
Currents.
Currents. Yeah, this thing here is just the current flowing along the edge E. So remember, this is where having studied electrical engineering helps you remember the formulas faster than the other guy, right? So I said that the current along an edge is the voltage across that edge divided by the resistance. That's Ohm's law. And then I said one of Kirchhoff's laws says that the voltage is the change in the potentials. So these disgusting looking expressions, they aren't disgusting at all, they're great, they're just currents. So the principle of minimum power is equivalent to something that's actually quite famous. It says that this stuff is equal to 0. What is that famous principle called? Just in case you know. Wise old men are smiling in the back, but not saying. Yeah? Huh?
Some of the currents are 0.
Yeah, it's called Kirchhoff's current law. So Kirchhoff got all the laws here. Proves you got to get in while things are still simple. Got 2 laws. Ohm, when he invented his law for resistors, sorry for the pun, he faced some stiff resistance against that. Yet there was actually someone who wrote a paper blasting him for this law, saying like, this is crazy, it doesn't make any sense at all. I don't know why, I didn't read the whole paper, but anyway, Ohm turned out to be right. No one remembers who he is anymore. So, I'd like to read that sometime and see what was so shocking about Ohm's law. Nowadays, we think it's very natural to assume that anything is linearly proportional to anything else before you have any better idea, right? You just say, oh, pretend it's linear. So Ohm's law is just would be like the very first thing you should guess. So it'd be weird to find that shocking. But anyway, maybe someone thought harder about it and decided it wasn't true. But anyway, it's approximately true for real-life resistors. So Kirchhoff's current law, it's just this thing that we said here, namely that that quantity over there left is equal to 0, or in other words, this, if you add up over edges whose source is in, current flowing along those edges, it's equal to the sum over the edges where the target is in, of the current flowing along those edges. This is supposed to be true if n is not a terminal. So the idea is, as you said, it's just that the total current flowing into any particular node, it's not a terminal, equals the current flowing out. And that makes a lot of sense now that we know that electrical currents made of electrons, and the electrons don't appear and disappear, so the total number, the rate at which they flow in here has to equal the rate at which they flow out. This doesn't need to be true at the terminals, because the terminals we think of as wires sort of dangling off into the rest of the world, and the whole way we get a circuit to work is by pumping current into it from outside. And so the terminals are where we allow current to flow in and out from the circuit to some other wires outside the circuit. So we don't want to impose this at the terminals. Okay, so the idea is that the principle of minimum power, or equivalently, Kirchhoff's current law, gives you a bunch of relations that have to hold, here they are over here, for the potentials at all the nodes that aren't terminals. And so if you were lucky, you could fix the potential at the terminals, and then these equations would determine what the potential is at the other vertices, at the other nodes. It's not always going to work. It won't. Sometimes you won't uniquely determine the potentials at the other nodes starting from these equations. But actually, usually, or out of lots of cases, you will. But we don't even need to worry about that. We just need to know that this is what nature demands. Nature just demands that these equations hold. So that those equations may or may not be enough to uniquely specify phi. That's up to nature, whether she's in the mood for being unique or not. It's worth making up a name for this difference, well, the difference of these two sides, which is, of course, 0 for the non-terminals, but it's interesting for the terminals. So if you've got a guy, I can't call it terminal little t, right, because we've got a little t here, so I'm sort of boxing myself in notationally. I'm going to call it x, even though there was an x earlier in this calculation. This is a new x. Okay. So if x is a terminal, you let what I sub x be the difference of these two quantities. So the current flowing into that terminal, edges pointing into the terminal, minus current flowing out. What am I doing? Too many letters. Suffering from too many letters here. Okay, that's right? So we call this thing the current at x. So current flows along wires or edges, but if you have a situation like this, I'm just not drawing all the inside of the circuit because it doesn't matter. There'll be certain nodes called terminals, and then, well, in some cases, there'll just be like one edge connecting to them. And then you can talk about the current. Let's see, what is this? This would be like I sub x, the amount of current flowing to that terminal from wires in your circuit. Right? It could be more complicated, right? So you allow all sorts of things. Anything not forbidden is allowed, right? So we allow weird things like that, and then you have to sum up these two currents and subtract that to get the current of this terminal. Or you can have terminals that have no edges connected to it. It would be terribly useful, but it's certainly allowed. Anyway, so although current starts out in life as a concept attached to edges, now we have the concept of current for terminals. And we also, of course, have the concept of potential at each terminal. So it's when you black box a circuit, when you refuse to look at what's going on in the inside, you're still able to see some stuff about what's going on. You're able to measure things that you can measure at the terminals. And the right way to think about it is that what you can measure is these currents at each terminal and the potentials at each terminal. So those are not freely adjustable because they need to obey all these equations that I wrote down. But those equations are precisely what describes the behavior of the circuit. They describe the allowed options for what the currents and potentials at terminals can be. And if you know that, then you know what your circuit can do, because all you do with your circuit, from this black box perspective, is take this black box and do things with it, like feed current into it or adjust the potentials at the terminals, and then see what that does, what effect that has on other terminals. So now we're all set to define the concept of the behavior of a circuit a bit more precisely. So the behavior of our circuit is the set of pairs. So pair consisting of a potential, it's a pair of two things, each of which is a function. A sorry, let me not write, let me write a different letter for that, okay? Because I've been using phi to mean this function on all the nodes. So I'll use its brother c to mean the potential at the terminals. That's the first item in our pair. And the second item will be currents at the terminals. So the current at terminals will be some other function. Call it J, because that looks like I, sort of. And that's the current at terminals. This is a long sentence. It's just getting going. So it's the set of pairs, not all pairs, but just the pairs that are allowed by the equations that we worked out. So the pairs that are compatible, sorry, I need to say it more precisely. So pairs for which there exist, what we're trying to do is trying to find potentials at every node and a current on every edge, which get along with what we've specified, but also obey all the relevant equations. I'll write down what, I wrote down a lot of equations, but I just want to write down ones that really matter. So such that, okay, so first of all, we want it to be true that if you take potential at a terminal, phi at a terminal, it's equal to the c that we picked. Okay, so we're trying to extend c to a function phi on all the nodes. That's the first sense in which things fit together nicely. The second, oops, sorry, I think I write subscripts for these kind of things. The second one is that the current at any terminal is what it's supposed to be, namely given by this condition here. So the current, we pick any old current at a terminal, but we say it's legitimate if it's given by the formula over there. So we sum over edges that go into that or point to that terminal, sum the currents, subtract then the currents going out away from that terminal. Right, so we don't quite say that we restrict I to the terminals and get J. So this is a little more complicated than this. But this is the way in which the currents along the wires can determine the currents at the terminal. Okay, that's like the bare minimum. But then the rest of it is that the laws of the circuit are obeyed. The various laws of the circuit hold. And basically, I could say such that the, and principle of minimum power holds, but there's a little bit more to it than that because I said I'm going to let myself pick any old potential and any old currents. Well, those are not independent choices. I want the currents and the potentials to be related by Ohm's law. So we want the current along each edge to be the change in potential along that edge divided by the resistance along that edge. Right? So this is sort of a combo of Ohm's law, Kirchhoff's voltage law, consequence of both of those. Kirchhoff has two H's. I think I've been screwing up.
You got it right the second time.
But not the first time? Okay. Okay, half the time I get half the H's, half the time I get all the H's. Maybe I should put in a few extra H's just so like make up for, yeah, be right on average. So I guess it's because Kirch, it means church, and that has one H, and then Hof, well, actually, without the extra F. Hof means like building, or something, or courtyard, or something. That's how I remember it, but apparently it doesn't work fast enough. So of course, this completely specifies the currents in terms of the potentials. So it means that we didn't ever really need to mention the currents if we didn't want to. It's just that it was easier to write out, and more pleasing to write out this equation in terms of the currents instead of solving for writing it in terms of potentials. And finally, the principle of minimum power, which sorry, blanking out. Yeah, I guess, well, right, we saw that the principle of minimum power was equivalent to Kirchhoff's current law at the nodes that weren't terminals. So I'll write it that way. So I'll just say that for edges, so N here will be a non-terminal. So for non-terminals, the current flowing in equals the current flowing out. Right, so this is for all terminals, this is for all terminals, this is for all edges. And then finally, Kirchhoff's law is supposed to hold for all nodes that aren't terminals. So this is, you can think of it two ways. Like I said, you can think of it as Kirchhoff's current law, or you can think of it as the principle of minimum power. Because we've paid enough attention, we've noticed that those were equivalent. I may have been in too much of a rush. I derived Kirchhoff's current law from the principle of minimum power by just calculating the derivative and saying it's 0 and this stuff is true. But if you think about it, because we're minimizing a function that sort of only curves up, that's an if and only if. When the derivative is 0, that's when this is true, then you're at a minimum. So these are equivalent, these two principles. Okie doke. So that's what it means then to say that you've got some currents and voltages at the terminals, and they extend to currents and voltages, currents and potentials all throughout your circuit that are consistent with the laws of physics. So this still looks sort of complicated, but one key thing to notice is that, well, the first thing to notice is it's either true or not. That's a pretty simple thing to notice. So either there do exist these guys or there don't. Okay, so there's some set of pairs for which there do exist them. And so that's what that will be our behavior. But then second of all, the other thing is to notice that all these equations are linear in terms of the currents and the potentials and the voltages. Well, currents and potentials are all we mentioned. So there's some condition that needs to hold, but it's a linear condition. So the set of pairs for which the condition holds is better than a mere set. It's a vector space. It's a linear subspace of the space of all possible functions like this. So that's part of having a linear system. Its behavior is linear. The set of things that it can do is not just any one set, it's a vector space, a subspace, in this case, of some larger space of things that it might do. So what we've got here, so the behavior, let me summarize that. So the equations are all linear. So the behavior is a linear subspace or vector subspace. Two words for the same thing. L of, so the space of possible potentials at terminals, r to the t. This is the set of functions from t to r. That's where our potential C live, and then the space of possible currents at terminals is also r to the t. So we're getting a linear subspace of this vector space. Of course, if you want to show off your deep knowledge of linear algebra, you write the cross sign in some other funny way. Rotate it 45 degrees and draw a circle for graduate education. So, but do the same thing. So that's what. That's not the definition of behavior, but that's a basic fact about the behavior. So now what we want to do is we want to show that the behavior is actually defining a functor from the category where the morphisms are circuits to some category where the morphisms are linear relations. So I'll sort of sketch how that goes here. So in fact, this is the punchline. The behavior gives a functor. I'm not going to prove it's a functor, but I'm just going to attempt to, I'm not even going to completely define it today, probably, but I'm just going to attempt to get the idea across of what it is. So it's a functor from res_circ to lin_rel, where these are two different categories. So res_circ is the one that we've been talking about a bunch. So an object in res_circ is a finite set of nodes. And then a morphism is a circuit made of resistors. And I guess I said this all before, just to pound it in. Right, so that's one of these cospans. So this is a morphism from the finite set I to the finite set O. The cospan, so it's a cospan in category of 0, infinity labeled graphs. Oops, I drew it as a span. I drew these arrows going backwards. Inputs and outputs are included in the body of the circuit. Okay, so that's the one I've been talking about ad nauseum. Okay, and so what's this other category, lin_rel? So an object in there is a vector space. Let's say it's like a finite dimensional vector space, finite dimensional real vector space. So the example would be that if you give me a bunch of points, give me a finite set, I can look at the vector space of current voltage pairs for that finite set. That's how the objects in here are going to get sent over to objects over here. And then a morphism. So a morphism will be going from some finite dimensional real vector space. I'm just going to say vector space, okay? A morphism will go from some vector space to another. It will not be a linear function. So this is terrible notation. So I will do what people do in this type of situation. Those who run into it. They put a little cross across that arrow. Basically, it's like, watch out. This kind of morphism is not what you think it is. It's something more general. So So it's a linear relation, not a linear function, from V to W. So what that means is it's a vector subspace of V times W. So, right, when you've got a function, you get a relation, sometimes called its graph, which is the set of all ordered pairs where the second guy is the function of the first guy. But not every set of ordered pairs comes from a function, even in the linear case. So linear relations generalize linear functions. Well, here I should say how we compose these morphisms. I spent like a whole class, it felt like to me, saying how you compose these kind of morphisms by composing cospans via push-out. But composing relations, luckily, doesn't take anywhere near as long to explain. It's just like how you compose functions, except you sort of don't worry about whether your sets of ordered pairs came from a function. So the composite of, so say you've got a linear relation from some vector space to another one, and then another guy, say S, vector space to yet another one. So I guess people, due to some idiot, decide to write composition backwards like that, right? So that's the composition going all the way from U to W. So this is supposed to be, whatever it is, right? It's supposed to be some subset of U times W, or going relation between guys and U and guys and W. So it's some set of ordered pairs. Down in here, but where you compose them just like you would functions, or just like you would relations, if you know about that, where we say that there exists a V intermediary, so to speak, an intermediate guy, V and V, such that, this is going to spill out of the parentheses here, such that UV is, U comma V is in our first relation, and V comma W is in our second relation. So there's some horrible failing in our educational system that talks a huge amount about functions and very little about relations. And so, you know, everyone who gets out of an undergraduate math degree knows how to compose functions, but for some reason probably they might not know how to compose relations, of which composing functions is just a special case. But on the other hand, if you tell them, you know, like, someone who's your father has a mother, that means you have like paternal grandmother, they'll get that idea, they'll get the idea that you can compose the relation father and the relation mother, get some new relation which is called paternal grandmother. So it's a completely natural concept, just somehow underappreciated a little bit. So David Ellerman back there thinks that even relations like get too much of the limelight. There are other things called correlations, which are also deserving of some time in the sun. And in fact, my student Brendan Fong, who's worked on proving the theorem that this black box functor is a functor, wound up loving correlations and using correlations to prove the theorem. So we will get to that to some extent later. But anyway, this is how you compose relations. So the idea is that this black box functor, you give it any set, that is any object in resistor, and it gives you a vector space, R to that set plus R to that set. This is the set of voltage, potential current pairs. Here, I'm just explaining how to think about what we did here. Potential current pairs. Psi, some potential on those on that set of points, J is some current at those set of points, which will become terminals for our circuit. And so then the big question is, what does this black box functor do to a morphism? So a morphism in res circuit is one of these circuits made out of resistors. I'm very used to working with spans, so I constantly get my arrows backward. So this will be a linear relation. I mean, I'm just saying stuff that has to be true, right? So it'll be a linear relation. So it will be some relation, linear relation from Ri plus Ri to Ro plus Ro. I guess now I'm showing off and using direct sum notation. And so what does that mean? Whoops, it's not a function, it's a relation. So what does that mean? It means it's a subspace of the sum of all four of these guys. And what is it? It's the subspace of allowed currents and potentials at the inputs and outputs of our circuit. So it's a subspace. By definition, it's going to be some subspace of Ri plus Ri plus Ro plus Ro. So it's some set of four tuples. And which four tuples? Well, like I said, it's the four tuples where you take a potential and current on your input terminals, and a potential and a current on your output terminals, and they obey those laws that I said they must. They give you a behavior, a possible behavior for your circuit. So I guess I could say the subspace of this thing corresponding to behaviors for our circuit. So black boxing says, forget the details, the inner workings of the circuit, which are all hiding in gamma. Just only think about what are the allowed potentials and currents on the input and output terminals. And then the real punchline is that this is a functor. So that if you compose circuits, sticking two circuits end to end, that it actually gives rise to the composite behavior. So here we're composing two linear relations. So the proof that that's true, don't worry, I'm not going to try to give it in the remaining negative 1 minute. The proof that that's true is long, I'll just say. And it's in this paper that Brendan and I are writing. Now I'm so flustered I can't remember the name of it. A compositional framework for passive linear networks. There are links to it all over the place and stuff. So I wish that there was a shorter proof. And there might be a shorter proof. The somewhat long proof, it's long because of certain nuances that I've tried to hide here. And the main nuance I've tried to hide here, although like George Washington, I cannot tell a lie, so I'm not very good at hiding nuances. The main nuance is that these maps sending inputs and outputs two nodes in your circuit don't need to be one-to-one. So there are some funny, weird circuits where you take two different inputs and sort of glom them together as being the same node in your circuit. That turns out to be very useful because if you allow that weird behavior, the category res circuit that you get has much better behavior than if you didn't. So I'll explain that sometime. But you would sort of pay the price for that good behavior by making apparently the theorem harder to prove. So there could be a much quicker proof, but the proof we have now introduces a lot of neat ideas. So I basically like it. I'm never going to give the proof in this seminar. You can be relieved to, because if I did, it would probably take the whole rest of the seminar. So what I want to do is maybe next time give you a couple of examples of all this stuff that I've illustrated. So I can calculate the behavior of some incredibly simple circuit, maybe some other simple circuit, and compose them and see that this works in that example. It's just to get a flavor of what's going on, and then we'll declare that we're done with that. And then if you want to really know why it's true, you got to read the paper with Brendan. And then we'll move on to the next thing, which is to actually understand this category of linear relations a bit better. So Jason has been working on the category of linear relations and wrote a nice paper sort of completely understanding that category. So we'll talk about that next, after a little example to sort of nail down the concepts here. Okay. Done?